Last week's quiz covered 2 chapters, so it was double in size of normal. The first half of the quiz covered resistive inductive series circuits, and then the second half covered parallel circuits. For the series circuits, number 1, how many degrees are the current and voltage out of phase with each other in a purely resistive circuit? Current and voltage are in phase with each other in a purely resistive circuit, so the answer is A, or 0 degrees. Number 2, how many degrees are the current and voltage out of phase with each other in a purely inductive circuit? They are out of phase with each other by 90 degrees. Number 3, in a resistive inductive circuit, so that is a circuit that has a resistive load and an inductive load, the voltage and current will be out of phase with each other by some value. It's going to be somewhere between 0 and 90 degrees. Number 4, this is basically an algebra problem. The formula to calculate inductive reactance is X sub L equals 2 pi times frequency times inductance, where 2 and pi are both numerical constants. F equals the line frequency in hertz, and L equals inductance in henries. The formula to solve for frequency is, so this is the correct answer, and here is the algebra. That's our given formula, and we need to solve for frequency. So X sub L equals 2 pi FL. Everything on the left side of the equation equals everything on the right side of the equation. So if we do something to the left side, and if we do that same thing to the right side, it's still an equation. They still equal each other. What we need to do is isolate F, or frequency, because that's what we're solving for. To do that, I'm going to divide the right side by 2 pi L. If I do something to the right side, I have to do the same thing to the left side for it to remain an equation, so I also have to divide the left side by 2 pi L. If I rewrite this whole thing and clean it up, we end up with frequency equals X sub L over 2 pi L. Number 5, in a resistive inductive series circuit comprised of an AC voltage source, a resistor, and an inductor, the purely resistive values in the circuit include the voltage drop across the resistor, E sub R, current flow through the resistor, I sub R, the resistance of the resistor, R, and true power, or watts, P. That is a true statement. Number 6 is similar. In a resistive inductive series circuit comprised of an AC voltage source, a resistor, and an inductor, the purely inductive values in the circuit include the inductance of the inductor, L, voltage drop across the inductor, E sub L, current through the inductor, I sub L, inductive reactance, X sub L, and inductive vars. That is also a true statement. Number 7, true or false? Power factor is the ratio of inductive reactance to resistance. So the question is basically asking, is power factor equal to X sub L over R? That is not equal. That is not a true statement. It is a false statement. If you look at Appendix B or the chapter reading, you will not find this formula. For number 8, we're given the formula for inductive reactance, and we're also given the formula for total impedance. The question asks, a series circuit contains a 75 ohm resistor and a 100 millihenry inductor. The applied voltage has a frequency of 60 Hertz. What is the total impedance Z of the circuit? This is a two-step process. I'm going to look at the second step first. That's this formula here. The question is asking for Z, total impedance. So that equals resistance squared plus inductive reactance squared. In the question, we are not given inductive reactance, so we need to calculate inductive reactance. That's this formula here, same as this formula here. So inductive reactance equals 2 times pi times frequency times inductance equals 2 times pi times 60 Hertz times 0.1 henries. That equals 37.7 ohms. When we use the 37.7 in the formula, we get impedance equals the square root of resistance squared plus inductive reactance squared. And the final answer is 83.9 ohms is total impedance. Number 9, we're given 3 different formulas for power factor. Power factor equals power over apparent power, or sorry, let me restate that. True power over apparent power. It also equals voltage across the resistor divided by total voltage, and it also equals resistance over total impedance. So number 9, a resistive inductive series circuit containing an AC voltage source, a resistor, and an inductor has a total circuit voltage of 240 volts and 144 volts across the resistor. What is the circuit's power factor in percent? So we get to choose which of these formula to use, and because we're given total voltage and voltage across the resistor, so we have total voltage of 240, 144 volts across the resistor, we're going to use this version of the formula. So power factor equals voltage across the resistor divided by total voltage equals 144 volts divided by 240 volts equals 0.6. In percent, that is 60%. Number 10. A resistive inductive circuit has a true power of 510 watts and a power factor of 90%. What is the apparent power? We have a hint here, use the decimal form of power factor in the formula. So from up here, we have this formula. Power factor equals true power divided by apparent power. We need to solve for apparent power. If we do that algebra, we get apparent power equals true power divided by power factor equals 510 watts divided by 0.9. So we're given the power factor of 90%. We are using the decimal form of power factor, so that is why it is 0.9. And we get an apparent power of 567 volt amps. For the second half of the quiz on resistive inductive parallel circuits, this is the same circuit and the same questions that we had in the homework for the parallel circuits. So I am not going to repeat that here. If you want to see a review of the second half of this quiz, please re-watch the homework review for resistive inductive parallel circuits.